In this video, we'll look at a situation of a pulley that has mass with a rope and a weight pulling down on it. So, first question in this one is conceptual. It's asking, is the tension in the rope greater than, less than, or equal to the weight of the bucket? If this pulley had no mass, then it would spin freely, the bucket would just fall, there would be no tension in the rope. If this were completely held in place and you let go of this, then the tension in the rope would have to exactly balance the weight from the bucket. So if it didn't move at all, then the tension force would be the same as the bucket weight. If we give the pulley some mass and let it start to accelerate, so when I let go of it, it will accelerate, but not at 9.8 meters per second squared. It'll be lower than that. So that means that there must be some tension in this rope. It's less than the weight of the bucket, otherwise the bucket wouldn't move, but it's bigger than zero, because if it was zero, the bucket would just fall freely. So for part A, the tension in the rope is less than the weight of the bucket. Now let's calculate what it actually is. So I've drawn a picture, made up a list of our knowns, and the unknown that we need to find. We need to find T, the tension in this string. So let's see. The disc is held in place. It's spinning because this mass is pulling down on it. So there's going to be some acceleration. We can find the acceleration by using torque as I alpha. So the torque on this thing, torque is F times R times sine of theta. In this case, again, anytime you have a pulley and a rope pulling on it, that angle is going to be 90 degrees where the rope touches the pulley. So sine of theta is 1. What is the force? There are a couple of different ways you can look at this. We could take this as one system, that as one system. If we can get the acceleration here, we could figure out from this mass what tension is, and the tension is related to the angular acceleration here. What I'm going to do is actually use the whole thing as one system, and I'm going to say that this force isn't just the tension pulling on the pulley, it's actually gravity pulling on this mass. So there's an mg, gravitational force pulling down here, and that's what's turning this whole system. I'm going to look at the entire system of this little mass and the disk. So that force is little m times g. R, little r there, that's the radius of the disk. So the torque is mg r. Alright, that's what comes from this. What comes from this one? So the torque is I. In this case, we have two pieces. We have I of the disk plus I of the mass. You can add up moments of inertia, just like you'd be able to add mass. If these were two objects that were moving linearly, you'd add the masses. The moment of inertia is just the angular equivalent of mass, so you can add those as well. So I disk plus I mass times the angular acceleration here. Alright, so I disk, that's 1/2 mr squared, so that's 1/2, this is the disk we're talking about, so it's the mass of the disk, this one. M disk times r squared, that's the big R, r squared, plus I for the mass, for a point mass, it's just mr squared. So that one I just called m, r squared, times alpha. This torque is equal to that one. So all of this is also equal to mgr. We know all of these things, we know this, so we can solve for alpha. So alpha is just mgr over 1/2 m disk r squared plus m r squared. That is 71.7 radians per second squared. So that is the angular acceleration here. So given the angular acceleration, we can find out what the linear acceleration is. So the tangential acceleration is r alpha. So that, in this case, that's big R. So 0.121 meters times 71.7 radians per second squared. 8.67 meters per second squared. All right, now we know that the acceleration of this mass is 8.67 meters per second squared. And we know that net force is mass times acceleration. If I take this as the positive direction, then the net force, that's T minus mg, equals m times the acceleration. It's actually accelerating downwards. So that's times negative 8.67 meters per second squared. Now I can solve for t. .85 kilograms times 9.8 minus 8.67 meters per second squared. 3.22 newtons.